Hello. The purpose of this video is to just further explain and differentiate what an interaction is, which is an important part of factorial ANOVA. So first, let's review what a factorial ANOVA is. A factorial ANOVA, by definition, has to have at least two or more independent variables. So in this case, we see a drawing on the right where we have one independent variable. Let's just call it condition, and we have conditions A and B, and then we have a second independent variable. Here we're going to call them colors. The red color is group 1 and group 2. So what we are seeing is a 2 by 2 factorial ANOVA. Now, we don't know whether it's independent groups, repeated measures, or mixed, simply because we don't have further information. We just know it's group A and group B, and we have, conditions 1 and conditions 2. That information would be required by looking at how the variables are actually operationally defined. And let's look at a more specific example and then see how the interaction comes into play. So an interaction is defined as the extent to which differences in factor A are dependent on factor B. So let's say that we're looking at the success of an intervention. For example, let's say we're looking at whether or not a imagery intervention decreases anxiety. So our participants are going to be in either a experimental condition or a control, one of those two. And they're going to take part in an anxiety measure before they're in the experimental condition or control condition, and then after. So they'll experience some form of imagery condition, and we'll see if that actually decreases their anxiety. So what I'm going to draw is what's called an interaction chart. And I'll start by showing the control. Now, if you're doing an experimental study, which this study can be a true experimental study because you can randomly assign experimental and control, we would assume that both the control condition and the experimental condition would probably start off with similar levels of anxiety. And actually, to make my life easier, I'm going to actually put them up a little bit higher. So let's say that everybody has kind of high anxiety to start. So we can assume that it does not matter if you are in the experimental condition or the control condition. We assume that you're going to have a fairly decent amount of anxiety, and we'd expect them to be similar because randomization should get rid of group differences. Now, if you are in the control condition, you're not going to be exposed to anything that should actually decrease your anxiety. So we expect the line to go like this. Whereas if you were in the experimental condition, we would hope that your anxiety actually decreases. So we would see something along these lines. Where what we're seeing is the extent to which we see changes from pre to post. So from differences in factor A, as you see in this definition, the extent to which we see differences or changes in factor A are dependent on whether or not the person is either in the experimental condition or the control condition, or what condition they're in of factor B. That is showing an interaction. Visually, when you draw an interaction, what it would show is some form of non-parallel lines. So we have a couple of different options in that situation. You could see an interaction that looks like, well, what we had there was something that looked like this. We could have an interaction that looks like this. We could have an interaction going the other way. We could have an interaction going this way. The only thing that would not be an interaction, so no interaction, is when we have parallel lines. So an interaction or no interaction, they both increase, and therefore you wouldn't see any, or factor A, changes in A would not be dependent on B if you have parallel lines. So let's take a look at our example again and see what that interaction advantage gives to us. if we were to just look at what are called the main effects, look at the two independent variables by themselves. If we just looked at the pre-anxiety versus the post-anxiety, that would be the overall average anxiety at both times. And we saw that at average, we saw that we had relatively high anxiety. And then after the imagery, now the control stayed the same, but the experimental group went down. So on average, it went down, but maybe not as much as it did if we were looking at the experimental group by itself. So we do see overall average decrease from pre to post, but this post variable is the average of both the control and experimental because it's not looking at the other factor. Now, if we look at control versus experimental by itself, we saw that on average, the control had the exact same amount of anxiety, does not matter, pre-post. And we saw that the experimental condition, at the beginning they had high anxiety, it went down. So again, they'll still have lower anxiety than the control, but because we're taking into account both pre and post, we aren't seeing that much of a big diminishing factor. But as soon as we have what we did before, where the control stayed the same, and we saw the experimental go down, we can actually start to see, well, this is the extra information we are getting out of a factorial ANOVA. You could also visualize this in a bar graph. So in a bar graph, we would expect the anxiety levels to be similar for control and experimental at the pre-test, but at post-test, while the control group still has its high anxiety, we'd see the experimental would actually have much lower anxiety when only accounting for experimental at post-test. So I hope this video clears up interactions, main effects, and the advantage that interaction gives you a little bit.